Okay, so what we got to go over today, guys, are essentially the three parts of the Earth that interact in order to produce the climatic conditions we are familiar with. Those climatic conditions we're familiar with are the result of transfers of energy. Okay? Not mechanical energy like in the last unit, but heat now. Okay? So thermal energy is what we're looking at. How does it get transferred? Okay? What parts of the Earth are most responsible for transferring this energy from place to place? Just thinking logically about it, which part of the Earth does most of our weather and, as a result, most of our energy transfer occur in? The atmosphere. Okay? The atmosphere, that blanket of gases, okay, that is so thin, really, okay, surrounding the Earth, is where the bulk of the Earth's energy is transferred from place to place. All right? It is the reason why temperatures do not vary more than, let's say, 20 degrees from day to night, okay, on our planet. Whereas on the moon, where there's no atmosphere, temperatures between the day side of the moon and the night side of the moon can vary several hundred degrees. Okay? The atmosphere is what essentially traps a lot of that heat energy and keeps those variations from being so drastic. Right? So it's a really important thing for us to have. Not that the other parts of the Earth, the hydrosphere, that's all the water, okay, and the lithosphere, all the earth and stone and all that other kinds of stuff, are not important. They are, okay, but they work differently, okay, and they have less of a role in energy transfers. All right, so the things we got to get: understand the three parts of the Earth: hydrosphere, atmosphere, lithosphere. Okay, we'll look at what they are and what they're composed of. Okay, look at how energy on Earth is absorbed, used, and reflected. Make note of those three words. That is what can happen to energy that strikes the Earth. Only three things. Okay? It either bounces off the Earth and goes back out into space, or it is absorbed, okay, in which case there is an increase in thermal energy, or it is used. Sometimes used is also referred to as converted. And there's only one type of organism on Earth capable of converting solar energy into chemical energy. Anyone know what it is? Plants. Okay? This conversion, this use, is entirely accomplished through photosynthesis. If it were not for that process, the sun's energy would uselessly strike the Earth and do nothing. Okay? In order for us to get the chemical energy we need to survive, the sun's energy must be converted by photosynthesis into glucose. Without that process, no energy ever gets exchanged. Okay? No chemical energy. All right, and lastly, understand how the energy and the Earth interact to produce the conditions necessary to support life. Okay, and so we're going to look at things like the greenhouse effect, which probably up until now you thought was bad. It's not. Okay, it's not all bad anyway. Right? In fact, if it wasn't for the greenhouse effect, the Earth would be too cold to live on. Okay? So it's kind of good that we have at least some greenhouse effect. Obviously, we don't want it getting out of control, because if it does, we'll end up like Venus, where the surface temperature is over 500 degrees Celsius. Okay? Now, that happens when your atmosphere is made entirely of carbon dioxide and sulfuric acid. Okay? Luckily, ours is not, so our greenhouse effect isn't quite so bad. All right, the atmosphere. Okay? By far, the atmosphere is the most important part of the Earth in terms of capturing and transferring energy. Okay? Now, okay, the atmosphere is basically these layers of gases. The part we're most concerned with is the lowest part. Okay, the troposphere. That's where the bulk of our weather occurs. That's where the atmosphere is thickest. That's where there's enough pressure, okay, for us to stay alive. All right. What happens as you go higher and higher up? Let's say you climb Mount Everest, for example. Okay. What happens to the amount of oxygen available? Yeah, it thins out. It's not just oxygen, it's nitrogen too. Okay? The atmosphere simply gets thinner the further away from the surface of the Earth you get. Right? And certainly not having as much oxygen makes moving around difficult. Right? If you've ever seen what the guys climbing Everest look like, okay, when they're near the top, okay, they take like 1 or 2 steps and then they stop and rest for about a minute. And they take like 2 more steps and they stop and rest for a couple of minutes. These guys are not out of shape either. Right? These are guys who could run marathons back to back at sea level. Right? They are in incredible shape, especially the crazy guys who do it without oxygen. All right? Some people cheat and they wear the tanks and go up. It's a little easier then. Okay? But okay, these are guys who are in good shape. There's just so little oxygen, so little air in general, okay, that it's difficult for your body to absorb what you need. The other problem is, with less air above, there's less pressure acting on you. Okay? And we've all felt changes in atmospheric pressure. If you go up and down really quickly, you sometimes feel your ears pop, like if you're driving through the mountains, okay, or you're on a plane and you're descending or ascending, sometimes your ears will pop. Okay? And that's because with less air above you, there's less weight pushing on your eardrums and on your body in general. Okay? And we feel that as atmospheric pressure. At certain levels, if atmospheric pressure drops too low, some of the gases that are normally dissolved in your blood will turn back into gases. That is, bubbles. Okay? Do you suppose it's good to have bubbles traveling around in your bloodstream? It is not, because some of your blood vessels are very, very small, microscopic in fact. If a bubble forms in one of those really small blood vessels, it'll rupture, okay? And you'll start bleeding out of that blood vessel. Okay? If that happens in your brain, we call that an aneurysm. It's like a stroke. Okay? It's not something you want to have happen. All right? If you get it really bad over your entire body, it's referred to as the bends. Anybody ever heard of that before? Okay? Scuba divers get it if they come up from depth too quickly. Right? Because when they're at depth, there's way more pressure than there normally is on them. And so gases dissolve into their blood more easily. If they come up too fast, those gases boil. Okay? Not high temperature boil, they just bubble and they turn into gas again. And those bubbles get lodged in their muscles and in their brain, and it is exquisitely painful. Okay? Like people are essentially paralyzed with pain. Okay? They have to put them in a big tank, a big hyperbaric chamber, and increase the pressure and then slowly decrease it, sometimes over the course of several days, in order to safely have these people recover. All right, and if they get it really bad, okay, you'll sometimes see that they'll have burst capillaries in their eyes. All right, I mean, you've probably all had that at some point, right? You get a blood vessel that bursts in your eye and you get that kind of red spot. Okay, imagine that over your whole eye. Okay, inside your eye even. Okay, really, really delicate blood vessels are most susceptible to damage by changes in pressure. Okay, so atmospheric pressure is really, really important. All right, in fact, for mountain climbers, the atmospheric pressure is very evident when they're cooking. Okay? At sea level, what temperature does water boil at? Boil. 100. Right. Okay? Boils at 100 degrees Celsius. Well, on Mount Everest, when people are making soup or something like that, if they're up at like Camp 4, they have to eat it while it's boiling because it boils at about 65 degrees. Okay? There's so much less air above them that there's not as much pressure keeping this stuff in a liquid state, and it boils more easily. Right? If you take a pan full of water and you take it out on the surface of Mars where there's 1/100th of the atmospheric pressure of Earth, it just boils away, even though it's below freezing. Right? Imagine seeing water boil at like -20. Right? But it would happen on Mars because there's so little atmospheric pressure. So atmospheric pressure is really important for sustaining life. Okay? We have to have a certain amount of gas above us pushing down. Right? Does that make sense to everybody? Right? So the main one, you're not going to ever be asked about these other levels of the atmosphere. Okay? I'm not going to be testing that. Just know we live in the troposphere. Really, there's no point on Earth you can stand where you'd be out of that. Okay, even on the top of Mount Everest or the top of K2, the 2 highest points, you wouldn't be outside of the troposphere. Right? You'd be near the stratosphere, but not out of it. All right. So the atmosphere does a few things, critical things for us. All right. The nature of our atmosphere allows some parts of the spectrum, okay, that is some of the wavelengths of light that come from the sun, to come through and strike the surface. But it blocks lots of others. Why is that important? Is all the stuff that comes from the sun good for us? No. Okay? The sun is a giant nuclear furnace. Okay? There's lots of stuff that comes from the sun that is very bad. X-rays, gamma rays, okay? Things like that would fry us like an egg. Okay? UV rays. Some of those get through, but a lot of them get filtered out. Okay? The atmosphere does that for us. Right? And so what happens is sunlight comes in, some of the stuff gets reflected by clouds, some of it is scattered, okay? Some of it just deflected away because of our ionosphere, our magnetic field, etc. Okay, a lot of that stuff just gets filtered out and it protects us very well. Right? But a lot of that stuff, the visible light, the stuff we can see, the thermal energy, the infrared rays, they get all the way to the Earth's surface. Okay? As they go through the atmosphere absorbs some of that energy. If you absorb energy, your energy increases. Okay, everybody follow me there? All right, so if we absorb thermal energy, it gets hotter. And that's what happens during the day. As the sun shines on us, the atmosphere gets warmer. Okay, some of it hits the Earth, and some of it is absorbed by the Earth. What kind of things might influence how much light gets absorbed or how much heat gets absorbed by the Earth? Think about it. Ever notice how some things get hotter than others? What kind of things get hot quickly? Right. What you're made of or your color influences how much energy is absorbed. Ever notice how a black car is way hotter than a light car in the summertime? Especially if you got a black interior. Right? You got a black interior. Black absorbs all wavelengths of light, which means it gets hot way faster than white. White reflects all wavelengths of light. All right, so if I had two identical cars sitting next to each other, one black, one white, I'd be able to put my hand on the white car, but not on the black car. Okay, it would get way too hot because it absorbs way more energy than everything else. Okay, that's why in the wintertime, okay, not only do we have less direct sunlight, which we talked about before, but also the ground is typically covered in snow, and snow reflects away a lot of the incoming energy, right? And that doesn't allow the temperature to increase. So one of the reasons why, what do we put on the roads in the wintertime? And sand. Okay? By putting sand on the road, okay, I increase what we call the albedo of the road surface. Okay? I make it darker, and as a result of making it darker, it will absorb more energy. The salt helps because it lowers the melting point of the ice to the point where the darker kind of sandy surface I put on there will allow the ice to melt. All right? Yes, certainly there's the added benefit of the sand usually increases your traction as well, but it makes the snow darker and allows it to melt more quickly. Okay? Everyone follow me on that? Okay, so lighter colored surfaces are going to absorb less radiation. Okay, we call that albedo. That's one of the things we've really got to know. Okay, is that radiation, okay, that is energy from the sun or any kind of light energy, okay, is differentially absorbed based on color. Okay, other things that can happen here. So this diagram here is comparing summer versus winter. Okay, and you can see in this diagram here, the sunlight in the summertime, 70% of it is getting absorbed. Because first off, we've got plants that are exposed on the surface and they're carrying out photosynthesis, and that requires energy. Okay, also the surfaces are darker, so they absorb more thermal energy. Okay, about 10% gets reflected off of the water and 20% reflected off of the land surface. But in the wintertime, when we've got that increased albedo, okay, increased reflectivity, 85 to 90% of the incoming radiation is reflected away. Okay? It makes a huge difference in the amount of available energy to be covered in snow. All right. So you think about a place like Antarctica. Okay? Antarctica is the driest continent on Earth. It almost never gets any precipitation of any kind. Right? And part of that is because it's white, gleaming white. And it reflects away so much energy that the water cycle can't get going. Okay? The water cycle can't go because there's not enough energy to melt the ice and not enough energy to evaporate the water and get that water cycle moving. The only precipitation it receives come in from other places. Okay? Everyone follow me there? So albedo is a big deal when it comes to the amount of energy available for a certain area. All right. Okay, so atmosphere again. Gases present in the Earth's atmosphere help maintain the Earth's temperature and climate. Carbon dioxide, CFCs, chlorinated fluorocarbons. Okay, methane. Yeah, fart gas. Okay, ozone. Okay, nitrous oxide. Okay, all allow incoming radiation to get in, but they don't allow it to escape. What is that called? Nope. Greenhouse effect. This is the greenhouse effect. These are all greenhouse gases. Okay, we know carbon dioxide is the biggest one. Okay, that's a big greenhouse gas, but so is methane. So every time you fart, you're contributing to the greenhouse effect. Shame on you. Okay, keep it in. No. Okay. Okay. But methane is produced by a lot of bacteria. Okay, that are present all the time in making methane. Okay, and all of our kind of bovine type animals, cattle and pigs and all those kind of things, they make a lot of methane too. Okay, anything that eats primarily plants is going to have a different digestive process that makes more methane gas as a result, right? And so these things build up in the atmosphere. Okay, ozone, okay, also a greenhouse gas, but ozone has the added benefit of filtering something out. What is it? What does it keep away from us? Comes from the sun. UV rays, right? Okay, this is the stuff that protects you from the ultraviolet rays of the sun. If the ozone layer gets thin, then you can get a sunburn a lot more easily. Okay, there are presently 2 thin spots, commonly called holes, even though they're not truly holes, in the ozone layer. Okay, one kind of over the very northern part of North America, and one over Australia. Australia, coincidentally, has the highest rate of skin cancer of any country on Earth. Okay. Now, part of that is lifestyle. The Aussies love to be outside. They love to be on the beach. Okay, they have good weather. They spend a lot of time outside. But they also have one of the thinnest parts of the ozone layer, so a lot more UV rays get through, and they have very high incidence of skin cancer. But yeah, you'd fry. Yeah. Okay. If there was a hole in the ozone layer, way more UV than normal would get through. Now, I mean, the area over Australia, I mean, it's filled in a bit. There's been some recovery to the ozone layer recently, but 10 or 15 years ago, that was almost a hole. Okay, and they had really, really high UV rates. Like commonly, the UV scale in Australia could be like 9.5. Okay, like we consider high or moderate to be about 7. Okay, and they were typically well over 9. All right, so it was a big deal. You don't want to have that lack of protection, okay? Especially since back at that time, you didn't put on a lot of sunscreen. You guys are kind of the first generation that really takes sunscreen seriously, okay? Back in my day, your parents sent you out in the morning, and you came home at dinner time, and you never wore sunscreen at all, okay? And you never got burned, right? But now it's a lot different, okay? And it didn't take long. Basically, we had to remove the gases that we were putting into the atmosphere that were reacting with the ozone and depleting it. Okay? Yeah, primarily those were our CFCs, the stuff that was used in air conditioners and refrigerators and stuff like that. The refrigerants had CFCs in them, and they would react with the ozone layer. Now, CFCs are banned. Okay, and so if you buy a fridge, it has to have CFC-free refrigerant. Your air conditioner has CFC-free refrigerant. If you drive an older car, like let's say early 90s, not that any of you would drive something that old, but okay, if you did, and you had to get the air conditioner recharged, they have to take all of the refrigerant out because it has CFCs in it, and they would pump in the stuff that doesn't. Okay, so yeah, they've made some changes. Aerosol cans don't use the same propellants as they used to, okay, because those would react with the ozone layer, and generally that's been found and discovered, and changes have been made that have helped to remove those things. So there's been some recovery. It's a slow process, yeah. The production of ozone is very slow, and ozone is always breaking down as it absorbs UV light. Right? So we were accelerating the process we were accelerating it from below, and it was getting it from above, and it was thinning out fast. So now it's just getting it from above, and it can kind of recover. All right. So all of these gases essentially allow infrared or long wave radiation, okay, or heat waves, to get in. They strike the Earth's surface, they bounce off the surface, and then they head out back into space. But they hit this layer, the ozone layer, sorry, not the ozone, the greenhouse kind of gases, and they reflect back down. The more times those heat waves strike the Earth, the more of them get absorbed, and as a result, the hotter the Earth gets. Okay, without those greenhouse gases, the energy would strike the surface and bounce back off into space, and it would be a heck of a lot colder. Okay, because we wouldn't be able to retain that heat. Really? Yeah, we were just talking about that. Yeah. Yes, that's what we were just talking about. CFCs, refrigerants, all those kind of things. The propellants from aerosol cans. Okay. All right. Next thing, the hydrosphere. Okay, the hydrosphere is all the water on Earth. Okay, and by that I don't just mean the oceans. I mean rivers. I mean lakes. I mean water vapor. Okay, I mean stuff that's in aquifers underground. Okay, the stuff that you would draw out of your well if you had a well at your farm or wherever. Okay, all of those things are included in the hydrosphere. All the water that there is on planet Earth. Okay, and glaciers as well. Okay, even so not just the liquid, the solid stuff as well. Okay, ice would be included. All right, less than 0.1% of all the water that's evaporated from a certain area actually returns to that area. Okay, because once the liquid turns to vapor, it can be moved easily. Okay, the atmosphere is always in motion. Okay, and as a result, it can move moist air masses to other places. All right, so in the summertime when we get a thunder shower, okay, like we got the last few days, we've gotten pretty good ones. That moisture that's falling here, that wasn't all taken from here. Okay, that was taken from other places around here and sometimes places far away. Okay, rainstorms, can come in from long distances. Snowstorms in the wintertime. Obviously, we're not getting the moisture, okay, in those snowstorms from our area. Nothing's evaporating when it's below zero. Okay, but that moist air comes in from the ocean, comes up over the mountains, dumps on us. You can't really measure it, but you can track it. Like that's what the Doppler weather radar kind of does, right? It can track the movement of those air masses, and then we can say, well, yeah, that moisture came from over there. Yes, that type of transfer of energy is convection. Okay, so the movement of energy through a fluid, air is a fluid, okay, is called convection, and that's one of the things we're going to talk about in a little bit, actually. So you're getting ahead of me there. All right, lots of that water that falls on the surface obviously can be absorbed. Okay, that's part of the water cycle. We call that infiltration. It can run off, also part of the water cycle. Okay, it can be frozen, stored. Okay, it can penetrate down into underground hollows in aquifers and things like that, and be stored as groundwater for long periods of time. Okay, the big thing to remember here is the amount of water on Earth is constant. It's just not always in the same place on Earth. All right, but the amount of water that is here now has always been the same. All right, we're not losing water to outer space. All right, the amount of water that's on Earth is always here. All right, the water you drink today could have been drops of sweat a week ago. Okay, it could have been dinosaur urine 65 million years ago. Okay, it's always getting cycled. I know it's a pleasant thought for you, but okay, it's always getting cycled through the water cycle. Okay, turning from one thing to another. Right, but it's always been constant. All right, so here's our water cycle. I know you've been beaten over the head with the water cycle since you were little. Okay, but we're going to do it one more time. We're going to talk about the really technical kind of parts of it here. Underground, yes. Essentially, yeah. And it's not like a lake, okay? An aquifer isn't, like people get this idea of these underground caverns full of water. That's not really the way an aquifer is. An aquifer is more of a saturated zone. So you'd have underground, you'd have like rock, kind of porous rock and gravel and stuff like that, and then that layer would be filled, the spaces would be filled with water. So you drive a pipe down into that, okay, and you can draw the water out and leave the rocks behind. Kind of like that, yeah? Right. Lane, can I have you just turn off that front bank light so we can see this picture a little better? Thank you. All right, so with the water cycle here, there's two ways for the liquid water to be turned into a vapor. Okay, evaporation, which is solar-driven, okay, direct transformation of water into vapor. Okay, or there's what we call transpiration or evapotranspiration, and that is water that evaporates from the surface of plants through the process of photosynthesis, like we talked about in Unit 2. All right, so transpiration is another way for water vapor to get into the air. The end result is there's water vapor in the air after those two processes. Now, when we get that water vapor in the air, it moves up. Okay, and as it moves up, it cools and condenses back into liquid water. All right, that liquid water can fall as snow. Okay, if it freezes again, hail, rain, whatever. Okay, it'll fall back onto the earth as precipitation. So this process here is condensation, Okay, and then we got precipitation, and once it strikes the Earth, it could be stored. Okay, it could be stored as ice and snow on a glacier. It could run off. Okay, runoff will eventually reach the ocean. Okay, or it could infiltrate. Okay, and that's probably a new term, infiltration for you. Okay, infiltration is the process by which water percolates down through the soil and into underground areas and is stored as groundwater. Okay, and then there's other various types of storage. Freshwater storage, lakes, ponds, sloughs, wetlands, okay, and obviously, okay, oceanic water storage. All right, questions on that? Dom? Yes, distillation. Boil it. Boil it off and condense the vapor. That's the other way. Okay, so all of them are quite energy intensive. Obviously, reverse osmosis not as energy intensive as distillation. Distillation is tons of energy because you got to heat it up, right? All right, so most of the Earth's water, 97%, is saline, okay, or saline or whatever, salty. Okay, it's salt water. It's in the oceans. The other 3% is fresh. That is the 3% that the entire population of humankind depends on. Okay, because we can't drink salt water. Our kidneys don't work that way. Right? Whales can. Okay, fish that live in the ocean can, but we can't. All right, we don't have a kidney capable of filtering out that salt. So we've got to have the fresh water. Okay, now of that 3%, 3/4 of that 3% is frozen. Ice caps. Okay, Antarctica, the glaciers, Columbia ice fields. Okay, all of that kind of stuff. So it's locked away. Luckily for us, we live where it runs off to. Right? So we have a very ample supply of water. If water were money, okay, Canada would be the richest country on earth. We have more fresh water than any other place. All right. Hopefully no one starts a war over water or we're coming under fire in a big way. Okay? Because we've got lots and lots of it. Now, what that means for us though is we have to be mindful of where does that fresh water come from? Okay? Well, it comes from the glaciers. But what's happening to the glaciers? Yeah, they're receding. They're shrinking all the time. Okay, and not at a slow rate either. They are receding quickly. Okay, give you an idea here. This picture here is of the Robson Glacier on Mount Robson. Okay, this glacier, okay, you can see it down in kind of the floor of this valley, stretches out obviously past the end of this picture. Right? When we were hiking up to it, my dad and I came across a sign that said, in 1902. The Alpine Club of Canada marked this point as the toe of the Robson Glacier. That means the end of it. We're looking around going, where is the glacier? We couldn't even see it from where we were. All right? We had to walk 2 kilometers before we could see it. Okay? Another 1.5 kilometers before we were even with it. Okay? So in 100 years, roughly, okay, because this is 2003, okay, roughly 100 years later, that glacier has receded like 3.5 kilometers. Right? And that's only one dimension of its recession. It's gotten that much shorter, but it's also shrunk in terms of its depth. Okay? This glacier, you can see in the picture, used to take up this whole valley, used to go all the way up this mountainside here. Same thing over here. So imagine how much ice would have been in there and how much water would have been in there. Right? These things are receding quickly and we're not putting as much snow and ice back on them every spring. Or sorry, every winter. All right? We're losing water, losing ice all the time. So we have to be mindful of how much we may have left and how much we use. And of course in Okotoks we're very mindful of that. Okay? You can only water your lawn twice a week. Okay? You got all those these restrictions and things like that that make sure that we are careful with the volume of water we use. To the ocean. Okay? I mean, ocean levels are rising because the glaciers are shrinking. Okay? We know from, like sea records and ice core sampling and stuff like that, that there have been times where the ocean has been a lot lower than it is now, usually during ice ages when there was a lot more ice. Give you an example, less than 10,000 years ago, the entire area of North America was covered by what's called the Laurentide ice sheet. A kilometer thick sheet of ice covered all of Canada. Okay, 10,000 years ago. What's left of it? You can see out the window. Okay. No, because as that water runs to the ocean, it picks up the salts, right? It runs over rocks, it runs, along the ground, and that's where it picks up the stuff that's dissolved in it, right? And all that stuff gets deposited in the ocean. So as it evaporates and falls as fresh water, it does that again. Every time it runs back to the ocean, it picks up more solutes, more particulates and whatever, and washes them in. I mean, last year during the floods, you might remember what the water looked like? Right? It was just brown, right? It looked like a milkshake as it was running through the rivers. Well, all of that stuff goes somewhere, right? Okay? All that sediment full of salts and solutes gets washed to the ocean. So no, there's not going to come a point where if all those glaciers are gone, it'll be okay to drink the ocean water, because every time they go, they bring more with it. If you do, but we're talking reverse osmosis is fine as long as it's small scale. On a large scale, it's not going to supply all the water we would need as a society, right? All we use reverse osmosis for is for drinking water. You don't shower with it. You don't do your laundry with it, right? But you can't use salt water for that stuff either, right? The ocean level would rise a long way. Certainly coastal cities would be inundated with water. Yeah. Okay. Very, very deep. All right, the lithosphere. Okay, lithosphere is basically soil and rock. All the soil and rock on the Earth. Now, if we go back here, okay, looking at ways to transfer our energy. Okay, when we're talking about the atmosphere, okay, Alex brought this up. The main way to transfer energy through the atmosphere is through this process, convection. Okay? Convection is currents that get set up in fluids. Okay? Hot air rises, cold air descends. You guys have heard that before, right? That's convection. All right? The movement of a fluid based on differences in temperature. All right? So convection is the main energy transfer mechanism on Earth. Okay? That's the one that allows energy from the equator to travel up to the poles. All right, and vice versa, cold air to travel to the equator from the poles. It was because of this process, convection. All right, that process will also work in the hydrosphere, because the ocean, okay, and all the water are fluids. But the ocean isn't in contact with all the points on Earth. The atmosphere is. Okay, and that's why the atmosphere is more important in terms of transferring energy than any other part of the Earth. It's the only part that can touch every place on Earth. Okay, so as a result, energy from any place on Earth can move by convection through the atmosphere and reach other places. All right, that can't be said for the ocean. All right, we don't see the effects of energy changes in the ocean here. I mean, to some small extent we do, but not on a large scale. All right, everybody follow me there? Now, to an even lesser extent, the lithosphere. All right, energy can transfer through the solid part of the Earth, but it doesn't do it very effectively. Okay, if you think about this, if you've ever stirred really hot water with a spoon, okay, if you leave the spoon in there, does the heat eventually transfer through the spoon to your finger? Eventually, right? But it's not fast. Okay, it's a slow process. That process is called conduction. All right, and what conduction is if this is the handle of my spoon, okay? Within the spoon are all those little molecules or particles or whatever the spoon is made out of, okay? If this is the end of the spoon that's getting hot, these particles move faster, all right? And when they move, they run into each other, like people in a mosh pit. If you've ever been in a mosh pit, that's what conduction is like, okay? When people start moving around, they bump into other people, and they start moving around, and pretty soon everybody's swaying all over the place, okay? But it takes if you're standing on the very outside, you don't notice it as much. Where the people aren't as kind of dense, you don't notice it nearly as much. Okay? And there's enough people between you and the crazies that that energy isn't getting transferred to you. Eventually, it would work its way out to here. But that's a very, very slow process. So the solid part of the Earth isn't responsible for transferring very much energy because it just doesn't do it very well. Okay? Is it responsible for absorbing energy? Certainly. Okay? The solid part of the Earth is what essentially stops the sun's radiation. When it hits the Earth's surface, it either reflects, absorbs, or is... What was the third thing we said could happen? Converted. You just redeemed yourself, Cam. Okay? So it gets converted by photosynthesis. Those are the only three things that can happen. All right? But they all happen here, okay, on the solid part of the Earth. Now, most important part of the lithosphere to us, living things, is the very top layer of it, the soil. What's soil made out of? Don't say dirt. What's dirt made out of? And everyone's like, I don't know, I was going to say dirt. Yeah, decomposed stuff, okay? The remains of plants and animals, and what else? Because it's not just that. Broken down rock. Okay? Broken down rock is the main ingredient in soil. Okay? The stuff that's, dead organisms and, feces and whatever else, okay? All that stuff is called humus. Okay? All the stuff that comes from living things is called humus. That's a small part of the soil. Okay? The bulk of the soil, the dirt, okay, is decomposed rock. Rock that is slowly eroded, okay, broken down into small parts and then collected in places. Okay? Here we have lots of soil. Our soil is very thick. Okay? Why? Because of the types of plants that live here, and because all the stuff that wears down is in the mountains. And the rivers and stuff and whatever will carry it here and deposit it. Okay, when the glaciers pushed out, they cleaned a lot of it away, and then as they receded, okay, more of it got deposited. If you go down onto the floodplains, okay, around our rivers, you see that this stuff is there. All that thick stuff that made the river look like milkshakes last year, okay, is sediment. Okay, it's weathered rock, and when it gets deposited, it can turn into soil. All right, it's a slow process to build soil. All right, think of how slowly a rock breaks down. Right? Now, some rocks break down faster than others, right? Okay, sandstone can break down pretty quickly, but limestone breaks down quite slowly. Okay, granite even slower, right? But that process, it occurs over the course of time. Water gets into a crack in a rock and then it freezes. What happens to the rock? It cracks open, breaks. Okay, now I've got smaller pieces of rock. Okay, and those can eventually wear down. But we're talking thousands of years, okay, for that process to occur. All right, so soil is the topmost layer of the Earth's surface where plants can grow. It's an ecosystem because it contains both abiotic or non-living parts and biotic, living parts. Okay, so the abiotic components would be inorganic chemicals, air, water, okay, decaying material, and then the biotic components would be bacteria, insects, okay, things like that, the living parts. All right, in that picture, do you see any soil? Okay, a lot of people say no. They say they see rocks. Okay, are there plants growing in that picture? Yeah. Okay, soil is not always what we picture it. Okay, soil doesn't mean like potting soil like you buy at the store, the thick black stuff, right? Soil can be a lot worse off than that. Soil can be essentially rocks. Okay, anything that can hold some nutrients and hold some water can support the growth of plants. What's that? Sand's a soil, yep. Okay, it doesn't hold moisture very well. Okay, doesn't hold moisture very well, but it can be a soil. All right. In fact, when you build a green at a golf course, it's mostly sand. Okay, when you first plant it, it's mostly sand. All right, because sand it's got some plasticity to it. Okay, and it's easier for it to distribute. You just got to water the heck out of it. All right, once the grass gets growing, you still got to water the heck out of it. If you stop watering a golf green for more than a couple of days, it hardens up and turns brown. All right, you got to be mindful of it. Probably would be granite, marble, okay, volcanic rock usually, obsidian, okay, stuff like that would probably be the hardest rocks to break down because they have a hard crystalline structure. Okay, sandstone, like sedimentary rocks, typically break down more quickly because they're made up, they're cemented together as opposed to fused, right? Volcanic rocks are usually fused, whereas sedimentary rocks are cemented. Okay. Yes. All right, soil structure. You all dug a hole as a kid, okay? Don't say you didn't. You all dug a hole as a kid. You probably noticed there were layers to the soil. If you didn't dig a hole as a kid, you've probably seen when one was dug. Okay, if you've ever had a house built nearby or walked past a basement when it was being dug out, you notice that there's layers to the earth. All right, those layers are what we call horizons, and there are soil horizons. Each layer or horizon has got a different type of job. Okay, the O horizon is the organic layer. That's where you'd see the most, like, dead grass and manure and stuff like that. That's the organic layer, okay, formerly living material. Underneath that is the A horizon, or sometimes we just call both of these the A horizon together. The A horizon is the topsoil. All right, and the topsoil is typically where your plants are most actively growing, right, Drew and Cam? Okay, underneath that is the B horizon, or subsoil. What do you suppose the B horizon is made out of? Clay. Okay, if you ever dug a hole, you know eventually you hit clay, right? And then usually stuck in the clay are rocks. And if you keep going, eventually you hit rock, just rock. Okay, we call that the bedrock or the parent material. Why do we call it parent material? Because it's where the soil comes from. Okay, just like you came from your parents, that's the rock that broke down, decomposed, and became the soil above it. All right, so there's typically this progression as we go. You can see it in this picture here. You got topsoil, which eventually gives way to kind of clay, and then you can see rocks interspersed, and then eventually you just get to bedrock. All right, in some places the bedrock is very, very deep. If that's the case, the soil is very, very old. All right, if you hit bedrock almost immediately, you're looking at very young soil. So when you go to the mountains, the soil is thin. It hasn't been exposed for as long. It's very young, so it's not very thick. Here, soil's quite thick. Right? You would have to dig down several feet before you were starting to encounter significant amounts of bedrock. Okay. All right, so A horizon, topsoil, mixture of decomposed rock, living organisms, decaying organic material. It's typically the darkest horizon. All right, it isn't always black. Okay, some places have different colors of topsoil. That color is determined by what kind of rocks were broken down in order to make it. Okay, here our soil's not really black, it's kind of a lighter brown because typically our bedrock here is made out of sandstone. And when sandstone breaks down, you get sandier, lighter colored soil. If you go further north, it's darker because the bedrock there is more limestone and it breaks down into finer stuff that's darker in color. Okay, if you go to PEI, their dirt is red. Okay, you can get the PEI dirt shirt. They essentially make mud and then they put white t-shirts in them and it stains them brown. Okay, and they sell them to tourists. Okay, they have red kind of soil, red colored soil because of the shales and things like that that are there. Okay, and so they're, in fact, even their pavement in a lot of places is kind of red in color because they take the rocks that are native to the area to make the pavement out of. All right. Okay, after the A horizon is the B horizon. B horizon is typically clay. All right, almost entirely clay. Clay tends to be lighter in color, bordering on reddish. Okay, the reddish is kind of an oxidized color. Okay, not a lot of free oxygen in there. Not a lot of biological activity going on in there. Sometimes roots will go down into there, but it holds on to moisture really well. You probably notice that you rarely encounter dry clay. Okay, that's because clay holds onto moisture really, really tightly. So tightly that plants can't even draw it out with their roots. Okay, and then below that, okay, you can sort of see the progression here in this hole. All right, you've got topsoil, and then as you get lower down, rocks become more and more prevalent. The rocks are broken down, but as you get lower, the chunks of rock get bigger until eventually you're into bedrock. Okay, down at the bottom. The C horizon is that parent material that all of it came from. All right, solar energy. You know what? I'm going to give you guys about a 2-minute break here. Okay, you need to recharge a minute. 2-minute break. Okay, I'll give you a 2-minute break before I go on to this next part here. Okay, solar energy budgets. What we mean by this is what happens to the solar energy that strikes the Earth. How does it get distributed? Okay, which places get more of it? What happens to it once it gets here? All right, so when we're looking at this diagram here, on the left, okay, so we've got incoming solar radiation at the top of the atmosphere is 7 million calories per square meter. All right, a calorie isn't very much, 1 calorie, okay, in terms of energy. If we're looking at it in terms of food energy, okay, you could survive on around 1,500 calories per day. You probably wouldn't be all that happy, but you'd survive on 1,500 calories a day. Okay, well, this is 7 million calories per square meter per day. All right, that's what hits the top of the atmosphere. So if you were standing outside the top of the atmosphere with no spacesuit on, you'd be in trouble for a couple of reasons, and this would be one of them. You would fry. Okay, this is a ton of energy that would be striking you. You're about a square meter. Okay, that's 7 million calories in a day. That is gonna cook you, right? And that's not what we want. So we obviously don't want that much energy striking the surface of the Earth either. It would be way too much. The Earth would cook. Okay, so a lot of it gets reflected away. Okay, some of it gets what we call backscattered. All right, what that means is certain wavelengths of light don't come down to the Earth's surface, but they don't necessarily reflect either. They get scattered. They go in all different directions. Okay? Now I'm going to ask you a weird question. It's going to seem out of place. Why is the sky blue? What's that? Okay, someone said, because is that what you were thinking, Phil? Yeah. Yeah, someone tells you that somewhere along the way, but it's a lie. Okay? The sky is not blue because it reflects off the water. What color is water? It's clear. Water's clear, people. The water looks blue because it reflects the sky. The sky is blue because the atmosphere scatters blue wavelengths of light. Okay? Just the gas composition of our atmosphere causes the visible light that is in the blue wavelength to go all over the place. Okay? It scatters it. It reflects it randomly in different directions, and as a result, the sky looks blue during the day. Does the sky look blue at sunrise and sunset? It does not. Okay? It's orange and yellow and red. Why? Because as the sun gets lower on the horizon, it's not passing through as clean of air. Okay? Closer to the horizon, it's passing through more smoke, particulate, and pollution. And as a result, red and orange wavelengths get scattered more, and so the sky appears red. Okay? If you look out over to Calgary, you've probably seen this sometimes when you're driving into Calgary from Okotoks, you come over the hill, and there's that brown layer over the city. Okay? Photochemical smog. Okay? Those gases tend to scatter different wavelengths of light, appearing greenish brown, undesirable and gross. Okay? Everyone follow me there? So the sky is blue because of this backscattering effect. Now, fortunately, blue and violet and ultraviolet all tend to have this happen to them. We don't want the ultraviolet to get all the way down, otherwise we'll get a sunburn. Okay, so that's a good thing. They would have still been, it still gets red just because the atmosphere is thicker and the angle of the incoming light is different. And typically, you still have ash and smoke from forest fires, volcanoes, etc. that's still present there. Okay? Essentially, it's traveling through more atmosphere to get to you. As a result, it has to travel through thicker materials, particulate and whatever, and so you're going to get redder skies. No, the electromagnetic field of the Earth doesn't have any effect on the color of the atmosphere. It can make the northern lights, but that's entirely different. That has to do with it slowing down like solar particles. Okay, they strike the solar particles that come from the sun. Essentially, the sun spits out not just light, but also particulate. Okay, and that stuff comes to the Earth and it strikes our magnetic field and it slows down. And when it slows down, it gives off its energy as light. That's what we see as the northern lights. When they hit our magnetic field, they slow down and fall and tumble, and then we see the light that they give off. All right. So when you see the northern lights, that's a good thing. Okay? It's a sign that our electromagnetic field, or just our magnetic field actually, is working. Okay? It says you are protected from the sun, no matter how nasty the sun decides to get. Right? We see northern lights when the sun is more active and spitting out more of that kind of those particles. No, there's periods where the sun just spits out. Like if there's a prominence, if you've ever seen one of those solar eruptions, okay? I'm drawing a blank on the correct term for that, but okay, when there's a solar event and it spits out a whole bunch of harmful particles, that stuff strikes the Earth and it makes the because that's where you see the magnetic field's evidence more. Okay, because it emanates from the two poles, right? The magnetic field emanates from the two poles, so you see more evidence of it there. All right, so back to this here, guys. We got the backscattering. We've got reflection by cloud. So 100% of the stuff that's coming in, okay, we've got already more than a quarter of it reflected away, okay, or scattered by our atmosphere. Okay, 16% of that heat gets absorbed by water vapor, dust, and carbon dioxide. Okay, 3% of it by clouds, and then we've got the stuff that strikes the Earth's surface. Okay, 4% of that reflects off the Earth's surface. 51% of the incoming radiation is absorbed by land and water. All right, so our atmosphere does a good job of getting rid of half of that incoming solar radiation. All right, thinner atmosphere means less of that. All right. Okay, outgoing radiation. So the stuff hits the Earth, and it's got the stuff that reflects off, or the stuff that hits the atmosphere, whatever, it's got to go back out. Okay, so we've got emission of light, okay, and heat by essentially the same sources. All right. All right. So without a doubt, okay, the main source of energy for all life on Earth is the sun. All right. If you are even driving your car, okay, your car is solar powered. Believe it or not. All right. So if ever a real environmentalist comes up to you and starts giving you a hard time about driving a gas-powered vehicle, you can tell them it's okay. It's solar powered. You're not really lying. Where'd the energy from your gas come from? Yeah, it came from the sun. Fossil fuels, right? You've heard that term before. Okay, the fuel we use was captured sunlight by photosynthetic organisms about 350 million years ago. All right, they captured energy from the sun. They used photosynthesis. When they died, okay, they got buried and compressed and altered chemically by heat and pressure and turned into natural gas, crude oil, coal, all of that kind of stuff. All of those fossil fuels represent stored solar energy, long-term storage of solar energy. Okay, so yes, your car is actually solar powered. Feel better about yourself now. Okay, yeah. I'm not saying that you don't pollute. You do. Your car pollutes, but it is actually indirectly solar powered. And as a result, so are you. Okay? If you eat plants, or if you eat animals, or if you're like me, you like both. Okay? You're still eating energy that came from the sun. All right? The plants converted it into sugars, and either you ate the plants directly, or you ate the animals that ate the plants. Or you ate the animals that ate the animals that ate the plants, or wherever you are on the food chain. Okay? Depends. All right? But in the end, all of that comes from the sun at some point. All right. Are there other sources of energy? Yes, but they're so small as to be practically non-existent compared to the energy supply from the sun. Okay. So energy transfers. We talked briefly about these, but now we're going to look at them in a little bit more detail. Okay, within the atmosphere, local regional winds. Okay, we got this stuff, convection currents. All right, we talked about that before. Okay, air masses carry energy that we can feel. We call that sensible heat. Okay, as well as this stuff, latent heat. Okay, we're going to talk more about latent heat later in the unit. But what latent heat is the energy that is stored by water vapor. If I have a moist air mass moving towards this area from the ocean, it's not just carrying moisture, it's carrying energy. Because in order to get the water into a vapor state, did that require energy? Right, to take energy to evaporate water? Sure it does. Okay, well now when that water vapor comes here, when it condenses, what does it do with all that energy? Law of conservation of energy says it has to go somewhere, right? If it's going to lose it because it turns back into a liquid, that energy now goes into the atmosphere and it warms it up. Okay? Latent heat is energy that is transferred through water vapor from one place to another. All right? And we receive a lot of our energy through latent heat. Right? We get some energy certainly from the sun, but we also get air masses moving to us from other places on Earth that are warmer and that are carrying all of this moisture. Right? Think about this, guys. To transform 1 milliliter of water from a liquid to a gas takes 2,260 joules of energy. Okay, is that a lot? Okay, 1 gram of water. That's how much it takes. Okay, that's a huge amount of energy. How many grams of water do you suppose get moved in an air mass? A lot or a little? Lots. Okay, we're talking about thousands, if not millions, of liters of water. Okay, think about how much water falls in a thunderstorm. Okay, it's a lot of water. Okay, it took a lot of energy to get it there. So this is a large source of energy that can come from other places. So there's sensible heat and latent heat. Both of them are moved through the atmosphere because of differences in temperature. Okay, last unit we talked about the second law of thermodynamics. Energy flows from hot to cold. This is what causes convection. Convection is the result of the second law of thermodynamics. Okay? Heat energy moving from hot to cold brings other air masses to us and cycles air masses away. Okay? And so that's what we see here. This is conduction. It's a way better drawing than I showed you a minute ago. Okay, I got heat at this end. The particles are moving very fast, but you can see over here the particles aren't moving as much. Okay, but over the course of time, certainly this particle could hit this particle, make it move a little faster, and so on down the line. Okay, convection. Okay, you got hot air rises, cool air descends, and you get this circulation going on. Okay, on your main floor of your house, where are your heating vents? On the wall or on the floor. Okay? Why do you want them on the floor? That's where the coldest air is. Okay? We want them on the floor so that the hottest air, the air that's coming out of those vents, contacts the cool air and starts this circulation going again. Okay? We want to reduce the amount of stagnant air, so we set it up that way. Okay? That sort of makes sense? All right? That's why we have fans typically on the roof. They blow the hot air down and get things circulating. Okay? So that moving air feels cooler. Okay? So convection, like we said, convection's kind of the really important one. Okay? It's the biggest one. And then there's radiation. Any heat energy transferred by waves is radiation. Okay? Radiation gets a bad knock because everyone pictures gamma rays and turning into the Hulk. Okay? Not all radiation is that kind of radiation. Okay? The stuff coming from the fluorescent lights right now, that's radiation. Okay? Visible light is a form of radiation. Heat is a form of radiation. If you stand next to the campfire, radiation is hitting you. Okay? Because heat waves, infrared rays, are radiation. Okay? Anything that can travel in a wave is heat transfer by radiation. Okay? And heat transfer by radiation can be absorbed by dark colors. And it can be reflected by, if dark absorbs, what reflects? Light. Okay? Things to think about there. All right. Hydrologic transfers, okay, we talked about this water condensing and this latent heat thing, okay? We're going to keep coming back to that. The way that essentially the hydrosphere gets into the Energy Transfer Act is by moving this evaporated water around and having this latent heat get transferred. So that water vapor gets somewhere else, it condenses, okay, and it releases that energy. Okay. Through the lithosphere, again, it's mostly absorbing radiant energy. Right? And then conduction slowly transferring from molecule to molecule. All right, now, how many of you have ever baked potato before, like on the barbecue? What do you wrap it in? Okay, you ever notice that tinfoil's got two different sides? Yeah, it's got a shiny side and a dull side. Which side do you want to have out when you bake the potato? Nope. Dull. You want the dull side out. Okay, I've gone to barbecues where people obviously didn't know the difference. Half the potatoes are shiny side out, half of them are dull side out. I make sure I watch, and I want one of the ones with the dull side out because I know it'll be cooked all the way through. Okay, because the dull side absorbs more of the radiant energy from the barbecue. Not only does it absorb a lot, it transfers it through into the potato. It travels right through the potato. And then what does it hit? The shiny side of the tin foil, and it reflects it back into the potato again. Okay, if you wrap the potato properly, it will cook more than twice as fast than if you wrap it with the shiny side out. All right, so next time you go to a barbecue, watch for that because lots of people don't know. Well, some of you didn't know. Okay, shiny side in, always, always shiny side in if you're wanting to cook something. Okay, everybody with me on that one? Okay, that's just a way to harness this radiant energy thing. Right now, In the barbecue or in an oven, where's the hottest spot? Up top, because that's where the hot air goes. Okay? Now, in a barbecue, it's a little bit artificial because it does tend to be hottest near the burner, okay? But in an oven, certainly, okay, the top of the oven, things tend to cook a little quicker. You got to watch which shelf you put things on, unless you have a convection oven. And of course, a convection oven has a fan inside that evenly distributes the heat, and it doesn't matter which shelf you put your stuff on in a convection oven. All right, so all of these things that you've probably heard in your life before, okay, are applications of the things we talked about today. Okay? Things to remember from today. Conduction, transfer of heat and solids by particles running into each other. Convection, circulation, okay? Convection currents, movement, second law of thermodynamics, okay? Radiation, anything transferring energy by waves. All right. The other thing to remember, what are the three things that can happen to radiant energy when it strikes the Earth's surface? It can be reflected, absorbed, Cam, converted. What process does the conversion? Photosynthesis. Okay, these are things we need to remember. There's always questions on the unit and final exam about those particular topics. Okay, now, I tried to go through this kind of fast so I could give you a couple of minutes to sit down with your group, okay, and decide on some stuff with your climate graphs. So that's what you're doing right now. Everyone's books are open, okay, and that's what you're doing.